the DFT it's bringing, what challenges and how it's impact to the DFT, what the DFT roles there. So we will discuss about all those. Then we will cover the SSN methodology, which is recently and it's required for a large billion transistor designs. So we will cover that also, and then finally we will end on the thoughts and takeaways, what we can be continue for the further future research and all. So let me start by the design overview. So how typically we design the SoC? So first we come with the requirement. Suppose we need to design a chip for one of the car manufacturer, and we will come up with the requirement what he needs from that chip. It's required to monitor the entire processor, talk to multiple radars, talk to multiple battery management, and all kind of SOCs we have. So we will get it the requirement. What is the expectation from the customer or the manufacturer? Then we will translate those requirement into the architecture specs, which we call the AS. So this will design how it will be operating. So what will be the my supplies, powers, and all? What is the application? What all the requirement they will convert into the SOC architecture. Once that's decided and created a AS, then we will come to the logic design. When we are talking about the very log system, very log for the coding, right? So then we will start and translating that architecture into the design. Suppose we need a ALU, we need a CPU, we need a AI tops, we need based on whatever the application and the architecture we were talking, right? Based on requirement. So we will start getting it coded. We will have all those IPs, files, anything which is required to translate that architecture. That will be end goal is to fulfill the requirement which is the customer having the requirement. Okay, once we done the coding, then let's talk we have been reached at the end, or gate, marks, flip and all whatnot at that level. Then it comes to that verification. We do that verify. Suppose we have designed a header, whether the header is working and giving me the correct three input header. That's the kind of we are writing a test bench environment to verify and ensure that yes, the particular application we are able to get it. Then once we have that a good RTL which we require, then we go for the synthesis and implementation. Now this RTL will be get translated into the pure gates. Now nothing but it's a gates. They will get all entire floor plan and backend line of implementation all. Once we have done, we call it the tape out. Once we are doing the tape out, it goes to the fab. So fab will start creating. Suppose this was the should be fabricated and it was implemented with the 5 nanometer, 3 nanometer, right? So those will be start fabrication. Once it done the fabrication, it will becomes like as a silicon wafers. We call them as a wafer. It's having multiple dies based on the wafer size. It's a 12 inch, 10, 8 inch, and what kind of wafer, what kind of the required chip size was there, whether individual die was like 100 square, 300 square, how much. So based on that, number of dies will be there on this wafer. Once wafer arrives, we will do that manufacturing test on the wafer. We will screen out the good dies and bad dies, and then it will be good dies will be goes for the IC, which we call the packaging. Once this package part is done, we will again test that during the packaging whether something is not gone and broken. So this package is once good die, those good die will be sampled to the customer, and then one customer use and it will start create based on that requirement, and then it will be creating a bigger application where like it comes to the end more customer, which is like us, which is again getting a car. Suppose this was a chip for that car, right? So this is how the usual VLSI SoC design flow. This was the example for car. We can have similar example for laptop, CPUs, NVIDIA processors. All they are at the end are similar process. Only just that requirement is changed. The logic will change for that. Okay, if it's application of process. Yeah.
अच्छा अच्छा ठीक है
Okay. So coming to the manufacturing defect. So now while we were doing this fab, and we were creating these things, so how it does impact the DFT and where the DFT will come. So it will comes once we start this manufacturing defects. So why this happens? Suppose there are metal layers. So at the end, once this M1, M2, M3, M4, these metal layers, we have M10, M11, right? These multiple metal layers, they may have the impurity which may causing kind of a conductance between both the layer, and that's a kind of created a short circuit short. So that's kind of one a defect it's during manufacturing. If there is a metal line which was created and it's having a impurity in between, and this is creating a void like open, then that's a kind of impurity in which cause that opens. So like these are the two very basic defects we called shorts and opens. Okay. And then another one, like maybe if we see this was a transistor and this was a layer which have very thin narrow just connection, and then remaining are broken here. So this kind of all deformations which cause these are defects between a just extra thin layer of between two metal layers, which is causing a shorts also. So these kind of defects are very normal with respect to technology node, until unless the technology processes get completely, and this TSMC and all these manufacturers are keep improving their process. If this kind of defects are there for particular metal layers, suppose, right, they are start improving them based on those all feedbacks, all DFTs and all tech nodes, whatever the testing we are doing it. So all these has to be corrected, so and detected. That's the part of job for the DFT, who is ensuring we are detecting and we are not shipping these defects to the customers. So now I'm starting on the impact of defect. So suppose there was a short between this lithography process, right? So this was creating kind of short. It may be functional defect also, which can cause the logical failure. Suppose there was a AND gate which is always tied at zero, then AND gate is always giving you zero, irrespective of the input of that. So that kind of also logically converted. There can be a speed defect which may be detected today while we are doing the manufacturing, maybe detected after 3 years, maybe it's detected after 10 years into the field. So that's a speed defect. So that's we call it the slow to rise, slow to fall, that transitional defect. So these are the multiple transistor which are weak, so they will be our potential issues with respect to speed defect. Then there is a third one, leakage defect. Usually in industry we known as a IDDQ, current measurement. So where into the transistor there is a channel and drain, so that's getting created a resistive path in between those channels, and so that is leaking more current, which is substantially, and then that's become the IDDQ current measurement. So that's also kind of third defects which we're talking. Now we know there are multiple defects, how to be detect and screen those defects. So taking example, we have this SOC, we will create a input pattern. Suppose these are the stimuli which we need to be applied on a SOC. This is treated like as a DUT. We will have a output pattern and expected pattern. If once this device does not have a defect, suppose this AND gate does not have a defect, if I apply all three are one, then my output should be one. So I'm expecting here my output should be one when my input all are three are one. When my inputs are all like suppose 0, 1, 1, right? Then I'm expecting it should be zero. So now if it's a defective and tied to one VDD, then it will be always giving me one, even though I'm applying a zero here. So like that, we are treating this as SOC. We will apply the input vectors to it, and we will compare with the output vectors, and we will see that where we are seeing the defect. So this is how we are screening those defects. We have multiple patterns for that, like we talking all these defects like stucker defects, speed defects. So transition we call, leakage defects we have the IDDQ pattern to call them, to generate those patterns in such a way that we will determine these defect based patterns. So now coming to the fault model, which we were like three of them we were talking, like stucker, transition, IDDQ. So there, how this is like this having the surface any during the manufacturing is the impurity, which can be dielectric breakdown. Need to correlate the circuit behavior. We need a one good stimuli, what should be the output of it, and then we will see that if any during manufacturing, any defect, any dielectric breakdown, any impurities which are causing and making the process, and then we will able to detect those defective dies. Okay, so taking example here, so this is a very simple OR gate. It's a two input OR gate, A and B and C. It may have suppose a stacked defect here, may have a stacked zero here. So it can have the six defects, stuck at all stuck at zero on all three in these two inputs and the output also. It can have stuck at one on any of these and both and on the C also. So these are the six defects which are associated with a two input OR gate. Okay, so we will cover them, how we are detecting them. So these are the stacked fault, transition fault, path delay. We will have a circuit in the next slide. So we'll see that how the delay of those gates and accumulated and it's creating that and how we will detect them. Then there are bridging faults also, which is adjacent layers when we are going on single digit tech nodes. Then more and more metal layers are shrinking and they are coming to next to each other and then they create a kind of a breeze and open and shorts kind of breeze and then that's also causing those aggressor and victim behavior. Memory cells, they have the faults, so that is moreover analogy kind of behavior where the rails are not at the fast or at the slow which require. So those are the memory faults also we will see, and then IDDQ fault which we discussed that above. So taking example of the delay fault, suppose this transistor which is not stuck but it's have the capacitance, it will be slow to rise, so that we call it the STR, slow to rise, and then maybe that slow to fall also. So this is kind of expecting a behavior. It may comes like delayed, like then it's a slow to fall kind of behavior. So that kind of transition faults we have. So suppose this was the path, and then there can be path which is by one AND gate also. So suppose like this, right? So there are OR gate, and this also a valid path from this launch flow to capture flow. This also a valid path. So in terms of path delay, we are trying to be find out a particular. We are looking for this launch, then gate one, gate two, and then capture flow. So this the transition we are want to cover, and we are giving the specific path. Okay, I'm looking for this path to be getting covered, the transition launching from here, that then that's model become the path delay model. Okay, so like again it's the same, three input, two input and one output, and three faults slow to rise and three faults slow to fall on the A, B and C. So these are the delay faults which we are having. Okay, coming to the IDDQ, we were talking about if this channel have the defect, then my current will be start leaking more, and this resistance become less. So this is how this IDDQ start short between the drain of this P and N fact. So this is the IDDQ current, which is kind of defect we are detecting from the IDDQ, where we will stop the clock and resets on the capture, and we will measure the current between all these. So if it's a short, then my current leakage will be higher. So that's the how we are screening the IDDQ defects. Now coming to the bridge, and bridge is like when we are talking on the metal layer like M11 and M12, they are adjacent to each other, and these are kind of during manufacturing creating a channel. While we were done this 1 mm square, whatever the distance of one, right? But if during this defect it's coming more near, now the speed of transistor will be impacting here. So this kind of bridge faults getting created around it. There can be opens and corners also. So this is another defect. So all this comes in the bridging fault, and which affects that aggressor and victim. Okay, so now why we focus on the test is defective parts should not ship to the customer. That's the primary goal. Every company has that one into the mind. And why, if suppose any mobile phone manufacturer are shipping a bad die to customer and we are buying that phone, and then we will feel that credibility issue from that manufacturer, that company, okay, okay, these phones are not good quality, they are not runs for 6 months, 12 months, they will get it, and all these issues, heat issues and all other issues also, right? So that's a loss of credibility, how the DFT impact to them. Then there is a safety and performance hazards. So that's also if it's a leaking and we are not detecting, then it will impact those hazards also into the performance, which we see so many times. Some of the phones are start heating up too much also, because of there can be a manufacturing defects also which are shipping to them. And then high cost of fixing these, recalling and all are more costlier than the fixing it at the design. So a very simple rule of 10 which we call and we know to the industry, it's not absolutely, but it's a kind of, when we are doing the IC during the design, it might be a 5 cents kind of cost. When it's during test, then it might be a $0.5. But when it comes final test, all three try temp and all metrics, then the cost is maybe $5. And once we have done on the and it goes for the board and system, then it becomes a $50 cost and a $500 cost. And once we ship that bad die to the customer, then from in field if we start recalling, then that cost is much more, $5,000 kind of. So it's increased the cost. So the best thing is defect cannot be avoided. At the end we need to be have it, cannot be shipped to the customer a defective part. The good part is, as soon as we can able to catch the defects, or the cost is very bare minimum. So during design, we do design in such a way we can able to get it as maximum as coverage, so that we will able to detect all those defects. And then we, once we are at the testing, suppose that that's a when manufacture, then also if we are detecting it's very less than $1 kind of cost. But once we have done and start board designing systems and all, then if we are detecting that there's a bad die, then the entire system is getting thrown, and it's more costly basically. So that's the reason we focus on the test. And now coming on the test cost, which is recurring expenditure and directly influence the device cost. Yes, that part is getting added into the device cost. Directly it's reduces the gross margin of the companies also. So it's not that free, it's expensive. Still companies are looking more and more gross margins via the less and less test cost, but it should be a trade-off. Okay, and how the test cost determine? It's basically biggest factor is test time. How much time it's taking my pattern to be screen out entire defects like stutter, transition, UDFM, breeze, and IDDQ and whatnot. All stress test and all. So this all directly proportional to my test time. If it's a 1 sec, 2 sec, 5 sec, what is my test time? So with respect to that, it's directly multiplying the tester cost. Okay. So now coming on the technology, we are going 5 nanometer. We were there couple of years back 7 nanometer. Before couple of years we were there 16 nanometer. So when we are going this side, lower and lower technology node, what we are expecting? Increasing number of transistors on a die. There was a million transistor, which become billion, now trillion transistor, right? So number of transistor, number of gates are increasing. Then your test cost is also drastically increasing, because now suppose here I was having 1 sec, now it will be 10 sec, because in 1 sec we were testing the million transistor, now we are testing the trillion transistor. So it's not going in the same ratio, but that this will be also drastically 10 times the cost is increasing when technology we are growing the number of growing the more transistor on the same device. Okay, so how it and all, I'm just setting an example. It matters the test cost also, as well as it's a cheaper also. So both way we can see that why it's matter with respect to the technology. Okay, now one always a question which comes is, can we use the functional vector? Why we need at all a DFT? So I think we have covered, could have been covered in the previous sessions also, how it's a different the DFT with respect to the functional vector. Yes, we can cover, and I don't deny that the functional cannot be covered. Suppose I'm taking a just very simple AND gate example here, right? So this AND gate example, I have three inputs A, B, and C, and we have the Z output. Okay, we can create a truth table, and this is all eight possible combination. To verify a defect, a fault, we need all these eight vectors to be there. Now we come to that. If we have any of stacked fault on any of the input, we need a one vector. Okay, so let's start creating. we can have two both of them. So this we don't need that combination for DFT. This also we don't need. This also we don't need. 1010 010 011 we need, yes, to detect this as a A1. This we don't need again. This, yes, we need B, detecting the fault on B. This we need, yes, detecting the fault on C. And this we need detecting the fault on Z and all the A's. So this covers these four faults. This cover this remaining. Okay. So four faults. So all eight faults are detected hardly by the four vectors. What we require functionally? Eight vectors. So this is how half of the vector is already reduced when we are doing these things from the DFT. Yes, why we need a functional? To ensure that this AND gate is working correctly. And like that, there is a device. So those all performance parameter, all correctness, which can try only on the one die. To ensure that couple of very simple dies, we ensure that we are meeting the functional. But we are not testing every manufacturing dies with these eight patterns to increase our test cost. So hence, like similarly, if it's a 4-bit uh, counter, then it will be 2 raised to power 4. So it's basically a simple math of getting how many combination required. Otherwise, there will be a functional hole, and that is verification coverage will not be there for that. So that's a 2 raised to power n. But in the DFT, it was covered can be covered only by the 8 patterns doing the structural testing. So there are pros and cons of the both side, and we know where to be use that functional and where we need a structural DFT test also. Functional test verify only the correctness of design. So we need and sample and do the test on couple of the device to ensure that chip is designed whatever it's supposed to mean for the functionality. So that we do on sample devices. Okay, we require large number of pattern because to be cover all the functional coverage, the eight all possible combination was covered in case of three input AND gate. So no automation available because every company, every SOCs has own application. So the verification engineers generate and debug these functional faults and pattern based on the SOC. So no EDA, good EDA which can be automatically do that and generate and give the patterns what it need. No quantifiable metrics the way we have the coverage metrics and all that's available for the DFT. So this kind of metrics are not there. There are toggle coverage and all, but it does not sound that okay how much we are getting all transition and all at what speed and at slower how it's covering and all. In structural test, it verifies the correctness of manufacturing hardware. If suppose that AND gate itself is not designed correctly, AND gate that is then covered the verification part. Yes, the chip is not designed, but the part of the DFT is to ensure that AND gate is manufactured and that correctness if it's have any defective which can be detected by the DFT patterns. Need less pattern to detect that we talks about 4 versus 8 and 8 versus 16 for the 4-bit counter. Faster automated generation, and as because all are standard AND gate transistor and all, it does not matter to us on the DFT कि what we are testing it. It's a CPU or it's AI chip or it's a graphics card or it's a automotive processor. It does not matter to us. It's matter to us. It's a AND gate and OR gates and flops. So there are tools, there are ADBG tools and all. They can be understand the design, then they can be automatically generate those patterns. All those concepts are same, D algorithm and all. Based on that only they generate. They use lot of algorithms to improve the performance, less the runtime, less the pattern count and all. But eventually it's a concept of D algorithm only, which I think we have covered in some of the session how it works. And then there are quantifiable metrics which we terms like test coverage, fault coverage and all. So they are uniform and standard what is the coverage for that device, and then faster ramp up to volume production. Once we have all these pattern stable and tested across try time and all voltage, so then it's very quickly to be start for the production. So now we come that AS specification level. Then we go to the stage of implementation. Once the design is kind of looking solid and stable, we can be take it forward for the test. So this is the correctness of the functionality and spec. Okay, what we are supposed that comes under the verification. Once device is start implementing and then to the silicon detecting all this manufacturing and process, that's test which is designed for test. So here we start the design, here we will finish and we start the test once we have the silicon available. Okay, so this was the basic and overview of about why and DFT and its need of DFT and impact of. So now coming to the next part, DFT techniques. So and tester overview. So let's start from the stacker fault testing. How we are testing it. Suppose this is a one of OR gate. This is an AND gate, and we are having U3, which is again an AND gate. So we have this are the four inputs, and this is output. So maybe we have a stuck at fault on this one of the line of U2 gate. So now this is stuck at 0. Okay. So now always what we will receive at the output, this is 0, this is 0, and this is always 0. So irrespective of input, we always getting a output 0. So that's telling us this of the line is faulty. How we can determine it? Let's take example. We start applying the vector. So we apply this vector. Any of the one input is 1. We apply this 1 1, but this was stuck to 0. And now we are expected this will come 1, this will come 1, this will be output of 1, but this was the green is expectation, or but what we are receiving is red, which is the 0 because of the stuck at fault. So this is how we are activating the fault, and by this pattern, and we are detecting, let it be to be propagate at the primary output, and then we will compare. It's supposed to be 1, but now due to the manufacturing defect and any of those defects, it's translating, and we can see this is a defective die. Okay, now coming to multiplex flip-flop. Okay, so okay, we have the millions of transistor, which we can call them node. So we have those many nodes available, and to expose all internal node into the primary input and output, can we assume how many of the SOCs input and pads will be there? This is unpractical, and none of us can do that one and can have that one. So then, how the DFT matter is okay? We know this is a flop. Let's translate this flop into the scan flop. Okay, so we will keep this scan change concept. So this is flop, the next flop will be there. This output will be goes again SI of this flop, and then this is the scan enable. And so now this will be translating like you are building a scan chain after scanning session. So this was in my design. Okay, having the clock reset and all DRCs we have been ensured. So this part we have a entire SOC. Now once we done the scanning session, we have a scan input. From that we can bring the data 10111, whatever the data we will require for this cloud to be touched. We bring this data, and this is the one pad we take in the scan enable, and so this is the scan enable. Then it will take the data from this mux I1 and shift in and then shift out the data from this scan chains. Okay, and when we do the capture, then it will be doing. So let's go to the stack shift and capture path. Okay, so this is the clock we are giving. We apply the one here on scan enable, and we start loading all the flows. So now whatever we will give on the scan input, every clock tick cycle, it is going on the flow 1, flow 2, flow 3. Okay, so this part we call it the shift. So we bring the data to all flops and propagate. Now we are going into the capture mode. In capture mode, scan enable will be 0. So now scan enable is 0. Now D path of this mux will be activated. Now if we are giving a, and which is moreover a functional path. Okay, now we give the capture cycle. It will capture the value from D, and then again we will shift out. Keep the scan enable high, then my queue will start shifting out from this, and we will measure on the scan out. Okay, so this is the stuck at fault testing. Like this we are bringing the clock cycles. We can see 0 is there, scan enable 1, and then this went to the next clock 1, and this previous flop is loaded by 0, and in next cycle this 0 went to this flop second, and then this previous one was shifted to here. So like this, once we have done in the capture, then we can have that value capture from the combinational logic, and then we start again shift out. So this 0 1 1 is going out. So see, now 0 1, and then 0 is coming on third cycle, like this. Okay. So now coming to the transitional fault. So on transitional, there will be a change. So shift will be still same. So we are keeping scan enable one, and start propagating the data from scan input and loading to all those flops which are in the chain. During the scanning session, we will make all these flops chain. And now in the capture, we will have two high speed clocks pulse, which are nothing but as a launch and capture pulse. Okay. And they will be at the same functional frequency where the device is operating, to ensure any combination logic, any transistor which are not slow to rise, not slow to fall. These all transitional defects we are objecting, so we are doing launching them from this flow, this combo, then maybe it's coming and capturing here, or vice versa also. If this was a launch flop, then this may be the capture flop, then the value is coming from this flop to this flop. So all this transition we are ensuring, so consecutive two cycles, and then this, if it's a slow to fall, then it will be get detected on this cycle. Okay, so then it's again a shift out. It's a similar. So now what we call is the coverage. So we were talking about the functional and structural test difference, right? So how it's create the difference is, it's give a matrix which we do compare and standard matrix. So like example, test coverage, which is number of detected faults, total number of faults detected, and divided by total number of faults minus untestable faults. So suppose I have a thousand of faults, and a couple of faults may be untestable, like this was a marks which is always tied one, so it's always take the data from this leg to this is never used. Its fault is there, but whether any use case is there where this fault will be exercised, no, there is no functional scenario. It's a kind of redundant fault, blocked fault. So this kind of faults which we are telling total number of fault minus untestable faults. So and these are detected. How many out of thousand? Suppose 990 we have detected, right? And two faults we have been blocked by this. So then my matrix will be 990 divided by 1000 minus two faults, right? This is my test coverage. Similarly, coming to the fault coverage, it's a detectable divided by fault, total faults. It does not matter that these untestable faults are how many or not. So that's the matrix of fault coverage. So that will be become 990 divided by 1000. So these all are nodes which we are talking about those faults, right? So stuck at 0, stuck at 1. Similarly, there will be STR and STF. So these are the coverage metrics. Okay. And now coming, let's see, this is the wafer, how the tester looks like, and we call it the AT, automated test equipment. So these are the probe head. So on the probe head, we will keep this wafer place here, and these are the test head, and we upload, and there will be GUIs and interface which are like laptop and desktop. So from there, this is connected, and this is connected by this mainframe also. So now we are applying, and it's all power supply, all this test head which is required, that's the coming from the mainframe. Vector are coming from here, stimuli. So what we are design the patterns, and all we talk about that input patterns, right? So those all vectors, they will become, there are needles, these red needles we can see on the test head. So that will be probe on the SOC, like wafer looks like this. Okay, and this are we calling the probe test. Once it's identified, okay, these are my bad dies, we will throw these bad dies. Only the good dies we will do for the packaging. Once we done the package, again we are taking, it can be same tester, but this probe head will be different for this with respect to the wafer versus this package, and then we can be again place this package parts here, and we are doing the same testing, same vectors which were there on the wafer which will be on the package. So this is how this entire process work, and this all mainframes and all this will be giving those all environments which we require, like minus
Hello, sir.
c.
Hello.
Yes. Yeah.
Uh, Mr. Tarun Goyal, sir. Can you hear me?
Yes, I can hear.
So if you want, we can have a 10 minutes break if you want it.
We can have after it next slide.
Hello.
Yeah, we can have it after 5 minutes.
Okay. Okay. No problem.
Okay. So now we have all this environment like minus 40 C, 25 C room temperature, and 125 C hot. So all these three temperature, so kind of environment we can get it created on tester, and we do testing. We call it this 3T, try time testing, and we do the matrix testing also, which we call it the, if during the wafers also there can be multiple process like slow wafers, fast, FS, like this, right? So and so all this kind of, we call it the matrix units and try time. So all these testings we do and ensure that at cold, hot, and room temp, to ensure that all that manufacturing defects we are detecting it. We do, if it comes from the processor with respect to the auto, so they all are industry levels, what kind of the associates we are designing. In CPU, we maybe have the level 2, level 3. Okay, if it's a defective die also, okay, it's a phone. Suppose we are not using, it's not killing to anyone. But when we go level 4, then we need much more quality and less DPPMs to ensure we are not having more defects or dies, which are like we call the 0 DPPMs, right? And level 5 is more absolute, it's a DPB, which we talks about these levels. Okay, so coming to this yield, so yield is basically a fraction of good chips which produced during the manufacturing chip, and this DPPM we were talking, and they were like defective parts per million. So like 1 2 DPPM we target for the auto parts, and for, if you are talking CPU companies, right, they target 2 to 300 DPPM. It means out of 1 million parts, they are saying itself because of their test coverage and quality of DFT, they are expecting 2 to 3 defects, chips are shipping to defective. When we are coming to auto, then the testing is that much rigorous and that much invested into the test to ensure out of millions hardly 1 and 2 parts are defective. Okay, so that's it mean DPPM. Next is DPB. Now we start talking about DPB, how much defective parts we are having out of those billion parts. Okay, we can take a break here. Okay, then we will cover the second section of.
Thank you so much, sir, for your insightful talk. Let us have a break for 5 minutes. Will it be okay, sir?
Yes.
Okay. So we will be back by 12:25. Uh, by that time, if you have any question, please feel free to type in the chat box. We will take the questions. Yes, sir. Can we take it back? Mr. Tarun Goyal? Hello?
Sure. Okay,
Yeah.
so I think we can take a couple of questions there on chat also. Functional verification,
Yeah,
how we
some
doing
questions,
after
sir.
manufacturing? So we are not doing on every die after manufacturing. We do functional verification before RTL freeze and sanity of vectors we do before tape out, and couple of performance vector only we do on the silicon also, to ensure, like suppose the our cores are designed to be work on 2 gigahertz, right? So are this any of the cores we test, any couple of devices we test across temperature, across process, to ensure that they are giving the similar kind of 2 gigahertz performance which we are claiming, and that was the requirement. So they are only on the couple of devices. It's not that every dies we are testing with the functional verification vector. How we'll do the test, functional test, if we are having all combination of input, it may take huge time. Yes, absolutely, that's the disadvantage of the functional test, and it's a huge seconds of the test program if we start doing that way. So we don't do that. Again, it's a critical path, performance path, and particular application which we are looking and ensuring. So we do on the sample devices, and then remaining we are believing on the structural test, or maybe the SLT and kind of the system test which we require on the application basis. Okay. So anyone have any other question?
So if you have any more questions, please feel free to type in the chat box. We'll take the questions from there. Your slides are not visible, sir. You may
I'm
share.
sharing again. Yeah. Okay.
It's visible now, sir.
Okay. So now let's we talk about the 5 nanometer. What it means? It's the most advanced semiconductor node. Okay. And into the industry right now, in couple of years we will have the again another tech node like the 3 nanometer. Couple of years back it was the 7 nanometer and 16 nanometer technology node, they were their most advanced. So with respect to time and more slow, we are going towards the advanced nodes, and now it's bringing that own advantage as well as own disadvantage also. The good parts, transistor miniaturization is giving the lot of performance, which we are talking about gigahertz performance kind of expectation from the hardware, and then the energy saving also, because now transistor is miniaturized compared to the previous size. So now high transistor density, compact low compact size, low power consumption, improve performance. So all these benefits are there. Hence, industry is going towards that lower and lower technology nodes. Along with that, it's becoming now producing billions of transistor on the same area. Suppose that 50 square SoC was 5 year before and versus 5 year now, it's million of transistor is converted into billion of transistor to the same space. So then there is a defects and process which is now increasing. Okay, so how it's affect the yield? First of all, yes, yield management is tougher to for these nodes and latest and greatest. So if you remember one of the customer, I can take the name of them, but they were moved on the 3 nanometer. It's one of the branded company for the manufacturer, phone manufacturer, right? They moved to the 3 nanometer, and the yield of that was translating hardly 48%. It means 52% dies are bad dies because of the process. So those old feedbacks comes, they goes improves with the time. Couple of years it take, all those lithography and all the process will improve. Then this yield goes 70%. Then this yield goes 90% and all. So that's the how the process improve, and this all cycles included quantum tunneling, all these metals, it matters, electron migration and IR drops with respect to power as and heat. So and then timing closure and tool limitation also, now design become that much huge. So for every other tools also EDAs are there, so they are designing the tools, they start crashing also when we start loading that big and big devices, right? So that's also again another challenge, and closing the timing of all those billions transistor, it's becoming difficult for ST also. Have own advantage, own challenges. Every challenge is a new opportunity to solve. Okay, so how its impact and how it comes to the DFT. When we were went million transistor, we were testing here. Now we are testing the billion transistor. Here metal layers was like this. Now metal layers are like this. More dense metal layers, more defects, prone, more aggressor victim, breeze and all. These all things are start playing. And nowadays, if you talks about that new terms, if many of the people have been here, the silent data corruption. So all these things are happening, and this all has to be detected. How it matter to DFT is we went to the cell awares. Once from the 16 FFC and onwards, we are doing the UDFMAs. So that UDFMs was cell only, having every AND gate, OR gate. At the end, it's a transistor. In the transistor, it's a FinFET. Into the FinFET, it's a metal layers. All those information is translated into the UDFMs. Okay. Then it comes to the bridge and opens, which on the single digit tech nodes when we are talking about this, right? Bridge and open. So bridge is basically a unintended conductive path between two layers, two interconnects. Okay, and this occurs segments of physically disconnected between those layers was supposed to be connected like this, and but they have a defect and opens between these two layers. So that's a kind of open defect. We call them ICB, interconnect bridge defect, and this is interconnect IO. So there can be static and again dynamic. Static is kind of stacked and dynamic is the transitional kind of defect. Then coming to the TACA, which we call it the timing aware cell aware. So we are doing the cell aware. Along with that, we are doing the UDF from SDF also reading, taking every AND gate delays, how much this propagated, and based on that we are generating. It's a kind of superset of the SDD. SDD is just do for the gate levels. So and TACA does on the cell levels based on the cells UDFMs also. How these old effects translate at the end, they may be creating a OR gate, AND gate, which was cause the functional failure, can be hard, short, and opens in the vias. There can be a resistive breach also between them. So these all are defects, and there are more and more patterns, more and more fault which are getting increased. So at the end, if we were having for this tech node a number of pattern, this is patterns become 2n via the number of transistor which increase. Along with that, 2 and new patterns also via the new faults also which we are covering, right? So at the end it was the n pattern which went to the 4n. So now number of vector is increased. What it increase? It's increase the test time, which is into the SAC. What is increase? It is increase multiplied by the static cost. So then it's a test cost. Test cost increasing, it's a decreasing the gross margin. So it's not that the test is also free, and if gross margin is decreasing, or product price has to be increased. So we cannot believe with the defect, and we can, and it's not that we can be without this. At the end, it's a business, so which cannot be run without the gross margins also. So to do this is a new challenge, and then EDAs also keep it challenge to how we can reduce this 2n from the vector, how we can reduce this 2n, how we can we increase this DFT test, reduce this DFT test. Obviously, the worst is to just reduce the seconds in which we are taking. The one of the latest and greatest which we are covering today is streaming scan network SSN. So this was initially started from the Intel, which started scan test fabric STF. Then eventually it goes to Siemens company, which is one of the EDA test and one of the ATPG tool and powerful tool from their portfolio, and which is they have. So they have developed this tool and methodology. We will cover how it works and what is benefit it's bringing. So basically, high level, What it's doing is now size is increasing, more and more patterns is required to test multiple cores. So how we reduce that test size and without any other penalty? I'm taking one of very simple example. Suppose we have designed that we were talking those flip flops, right? We were having a clock and keeping the SI data when scan enable was high, correct? And this clock was some frequency. Suppose this frequency was 50 megahertz. If you talk to me a couple of years back, we call it the shift frequency. How many chains length and all there, and this cycles which we are bringing data to the device and then shipped out. So this is multiply by with respect to that once we convert into the ns. So that's translating into the test time. Okay, so this 50 ns is basically 20 ns. Suppose I have the 10 cycles shipped, so then it will be 10, and I'm just keeping the capture right now because heavily time is depend on the shipped in data and shipped out. So once second data is shipped out, then first data is loading like this, right? Previous pattern is, so it's a one time, so it will be calculated 20 ns. Suppose multiply by, I have 100 shifts cycles, so then that's a kind of test time it's require a one pattern. Right? Now to reduce, suppose this was coming, whatever the number it's coming, right? 2 microsecond. So to reduce this 2 microsecond, one way is we increase this 50 megahertz. Now suppose we make this is 100 megahertz. Now what will be the time period? It will be 10 ns and again 100 cycles. Then it will be become 1 microsecond. What is the cost? Now you need to meet the design at 100 megahertz, right? Timing closure is required at 100 megahertz. And these are only the timing path. What extra efforts it's bring? It will bring a lot of IR current also now because your million transistor is become billion transistor. So those many flops, like there was 1,000 flops, suppose, right? Now we are having 1K flop. Now it may be 10K flops like this, right? Per partition or anything we can take just example. So this are increasing number of flops. We are increasing frequency, di by dt, IR drop, and eventually we are ending on the power issue, vmin issues, and my patterns will be fail on the tester. We will not able to test. Again we go slower the frequency, or maybe we will slower the toggle activity, pattern count will increase. So this was, suppose earlier 10 patterns was required, now I reduce the toggle count, now 100 patterns will require. So at the end, my test time is getting compromised. What eventually Siemens come up with this concept is, okay, we will not give the hit to the STA, and we will not give the hit to this your partition and code level, whatever the adjacent togglings are there. We will give you the data in form of packets. Okay, and how it works is, taking example. So let's see that this is a my core A. Okay, this is again same EDT, like as usual EDT is there in last 20-30 years into the industry. It's nothing but as a compressor decompressor. So which talks, right, the less channels input and then internal chains. So we are giving the data. This they are calling it SHS, streaming scan host. There is a TDI which configure all these SSS. This red ring which we can see IJTech, TDI to TDO, and we are bringing the data on the SSN bus in. Now they are the packets, okay, and data is coming at the 200 megahertz. Okay. Now suppose it was going two cores, this one core and two cores. Now we will run this core at 100 megahertz only. But what we will do, rather than enabling two cores, we can enable all four cores. Got it? So suppose this was required and running at 100 megahertz. This is also running at 100 megahertz. We are not changing the performance of this course. Let it be meet ST also at 100 megahertz and let it be run at 100 megahertz. The both cores are running 100 megahertz. Packet was earlier coming on the shift clock of 100 megahertz. Now we are bringing data at faster. Okay, but we are not running internal cores at slower. We are running, sorry, not running internal cores at the faster. Okay, what we are running, they are running still at 100. So okay, I have a n number of channels. Suppose n by 2 was required by this EDT and n by 2 was required by this EDT. Now data was earlier coming n multiplied by 100, right? And this was consuming. Okay, this much data was coming. Now also this much data coming, but it's coming at the rate of 200. So now same n number of patterns, which is coming at the rate of 200 megahertz. Now n by 2 was used by this, n by 2 was used by this. So total how much it's used? N data multiplied by 100. So that much data they consume, but still we have 100 more. So now we will give the same n by 2 data to this also, this core, and n by 2 data to this core also at the 100. These cores are working still at 100 megahertz, but now all four simultaneously, all four cores are able to work. Okay, that's the one advantage. Now, why we are bringing a 200 megahertz? There can be a way. Okay, we need all four cores to be run together. Suppose this was require n by 2 channel, this was require n by 2 channel, this also n by 2, and this is also n by 2. Now, how many channels this require to run all four together? They require 2n IOs. Now, do we have those many IOs on SOCs? Answer is no. It's also additional cost. If SOCs has 2n, we can be use the 2n. Okay, but can it scale 4n, 8n like this? Answer is no. Those many IOs, we will not have always the flexibility when these tops are going like multiple of 50 partitions, 100 partitions. Now we are talking about 2 to 300 partitions per SOC. So it's just an example of four cores where we are targeting. When we are targeting like this kind of, then we can assume thousands, 5,000 kind of IOs requirement if we are doing that. We stopped doing this. What we started doing, okay, whatever the IOs are usually in the case of range of 100 plus minus, right, 50. So this IOs we are consuming, we have same number of IOs. We bringing the data at faster, okay, and running the course at slower. Okay, and how it can manage? It can analyze all the data requirement internally. If suppose these are very small cores, they don't require data, they may run much more slower also. They don't waste the packets. So that's whole computer architecture pipeline and all this risk, right? How this bus works at for the faster and faster frequency, right? This we are going. So now industry is bringing around 4 megahertz, 400 megahertz easily at the scan input from outside, but still internally they hardly run at the 50 and 100 megahertz. So they are not increasing, not in penalizing the local cores. They are consuming the data at a faster and distributing more and more parallel cores running concurrently. Okay, and this protocol IJTAC, which we call and the tool can program and all this host, which is IEEE 1687 IJTAC protocol. Okay, and how much it's benefiting us is like it's completely decouple the core level and chip top DFT strategy. The example, this was the four cores, right? So taking example, this was the four cores. We have placed this four EDT, and this is my big partition. I have suppose three channel input and one channel output. Okay, now we need to create a test plan or a DFT design architecture to do the testing of this core. How we can do? We maybe come up like, okay, this core is one smaller, we give a one channel. This is big, we given two channel. This is more big, then we have maybe given three channel. This is again small, then we have given one channel, one channel input to these edts, right? These are the three channels. And I am just creating a, or maybe let's have symmetric only, so then we will have three channel input and three channel output. Now this is the one channel input and one channel output. How we create a combination? I'm just taking, this is A, this is B, this is C, and this is the D. These are the four cores. One possible is we will run A plus B together. Then all three out of three channels will be used. Correct. Then second option, we run the this core D. All three channel will be used, and then we run the C core, and C is using only one channel. Then remaining two channels are wasted. Correct. Now we have designed. Some of the logic is moved during the implementation stage here to here or here to here. At the core level, we have to first ensure okay, what size of EDT we are designing it. Now at looking at SOC, we can say okay, anyway we are wasting two cores, two channels. We can give this as also three. We have given it three. Okay, we design suppose three. Now after next release we call, or maybe one request come up on requirement and architecture spec, we need to add one more IP on the A. Okay, now IP is added, more logic come, then our compression ratio get again disturbed. Now you are treating it as a small core. Now actual requirement of A is suppose three channel. Okay, now you again going and changing your planning. Okay, now my core A is require three channel. My core was B. Then my combinations will be, in first combination, my I'm running core A. Second, I'm running core B, or maybe again I do core C also again to bring one to optimize my test course. And then again I'm changing C and I'm changing A. Then it's again changing my combination B plus C. Then I'm using the third combination where the only the D core is getting used. Okay, so it's all depending on one core, which is again changing your core C and your entire test structure and your SOC also. So that was the limitation. Otherwise, what we will have penalty of this compression, which usually in the range of 100 to 125, the compression ratio, right? So this compression ratio is now become the 200, 300. We will start getting the EDD about those coverage issues, because now all this at the decompression side, more than compression, the chains are getting exor and coming out. So basically, we want to decouple and don't wait till that entire core, and we need a lot of time. This applications and specs which changes are coming, which is used to, it can come up. Suppose we have been have a one customer, for that we are designing a chip, and then we have seen that another customer is also looking interest, but he given that okay, give me this feature also, then I can consume. Now we cannot be design a standalone a one chip entirely only for a, and then for customer we again we are designing. What we will try to do is okay, we take this feature and we see that it can accommodate. We take that as a design change, and we design a one product which caters for both customer. Okay, and for this customer this feature may be disabled as it's not requested and it's not required to him, but it's a design cost is for us, it is a similar or in the same magnitude, rather than it's creating a new SOCs for that customer. Okay, so now because of that designs changes are coming, but now suppose we take the design change, it's require again to redesign SOCs. Then suppose we have been committed the customer 12 month, now we, because of this maybe 4 more month get added into the design cycle. So that's not good, right? Customer one don't need that feature, why it should get the penalty? That's the reason now this need to be decoupled. That core level versus the chip level. All this. So now how in SSN matter is, it does not matter all your grouping. Okay, you can do post tape out also, no matter to you. You are having a bus which is suppose having three channel. Okay, three channel is going to every host. You can design. Now this was consuming one only. You have designed EDT of one. Now request come up. This is now three channel. Okay, you give the three channel. This SSN bus will be give more package to this now because this become bigger. But you don't need to change entire design. You don't need to change entire your test plan. You don't need to entirely change your DFT for all this. So this is how it's help, and we are not worrying about cores. Okay, the core change comes, then it might be a days kind of delay rather than 4 months, right? And it's reduced the congestion also. Earlier, when we were designing the EDTs, so this was the 4 EDT, right? We were placing a channel marks. So this is my channel marks, which give the this input to this EDT, this input, and then this, and vice versa. Also taking a scan out, and then we are taking them out. So this was creating a lot of this crisscross also, and it's not like we call it the star connections, star based EDT implementations. Now it's a bus. How it looks like, this was the my SOC, this was the my course. Okay, I have entered from here, I went to here. If this core is used, fine. If not used, it's giving this bus like this to this core and this to this core. No crisscross. Any core don't use in the next associates can just a shorted path like this. So now it's a cleaner, and it's reduced all those congestion which was creating a star and the spiders, right? Like this. This all get resolved with this bus kind of architecture, which was heavily pin muxing earlier. Supported tile base and modular design. So what is the tile based designs are like, once we are designing this SOCs, so when we talks about the performance and course, right? Suppose this was the two course was added, then for the next time ECTA course, 16 course like this. So this all AI chips are basically heavy on the tops. We call that cores and tops, right? So those multiple tops can be added in the magnitude of 100, those tops. So all those are a physical partition and a one time. How many times you need a replicated, you can do those. So this is very good because now all are physically same time. You can apply same data to all tiles. So even though you don't need a new data, you are having a bus, you apply on same, and SSN support that one, and it compares on chip all the styles data, give you the pass fail. If you're good die, it's a pass. Take it, ship. If it's a fail, then just fail die. So just it's apply the data, having a on chip compare. It compares the data for, because it's a, again it's a hardware which add, but it's a using the 4 cores, 10 cores, 20 cores, right? So now it's a one hardware cost for all 20 cores. So in that case, we are not getting any scan out I was using, and we are just keeping the same data to all cores, broadcasting, and we are comparing on die, just giving pass fail. If we need to expose the scan out, we can do that for debug. Bandwidth tuning, we were discuss here. This was the one channel, two channel, one channel, three channel. It's bringing data three, but it see okay, this is my heavy core which require more pattern and more bulkier. It's give the data packet in such a way like it's a kind of tuning like I have a one tab. There can be large tab on it, and remaining are small. So like this, it may be giving the three drops. Remaining course, it's giving one drop at every cycle. And this is hungry core and bigger core. It give the packets in this way. So that's a bandwidth tuning, independent shift and capture. Now all these cores can run independently. When this core is maybe in the capture phase, then other core can run in the shift phase because that's the host is doing the job. So during capture, we are not taking any scan input. We are doing taking from the function path. Yes, at that time packets might be going on another core. So what eventually its help is, it helps to reduce the IR power also. Okay, so these are the couple of key benefits in terms of technical. Now coming to the impact. So this is the public domain reports which I'm sharing here for a moment. Like the Intel reported 43% reduction on the test volume and cycles using the SSN compared to traditional pin marking which we are using it. So similar kind of results are there for over SOCs also, which are benchmarking the industry standard, and we are capitalizing similar kind of test reduction 30 to 40% easily at our environment also for auto. So in and way, our test cost was increased, which was come down by using this SSN infrastructure and bringing the test more packets to the at higher speed and without changing the core level frequencies. Okay, and it definitely help with the DFT planning and implementation. Now we are not worries about that one. Okay, it will be a 4 month we are hard negotiation with business and all. We don't need. Okay, you are having a customer requirement. We can see that your margins will be higher if it's multiple customer, more volume going, then more dollar are coming. We look at like that in the industry. So, okay, fine, you do that whatever you need to do with the A. I don't need to change my DFT entire SOC. So we just take the consumption of A and that impact of days and we will move forward for that. So this is how it's simplify of the DFT also and accelerating time to market for chips. Okay. So there are a couple of thoughts and much more things. So maybe one more couple of things I can start like the test time and test volume. So these are the two critical dollar item. So which we can solve via SSN, we can solve via serializer, deserializer, DDR. Bringing all these things are there in the industry. We can look across, and there are a lot of R&D opportunities in those domains. At the end, it's a very huge impact. We have the cell aware that area where breach open metal layers and how defects and kind of those things. So we can do lot of studies, lot of innovation, lot of future works on those areas also, which is anyway going to be aligned with the Moore's law of that tech nodes. So that's also another key area. We have the security. So nowadays AI and all we are talking. So if we talk in the ages before, years before, computing 2 raised to power 56 could have been harder and bigger and doing, but solving those things via AI processors and gens, right? With those kind of performance, it could be easily to break also. So that's also a area where, with respect to DFT also, which having the access to the functional paths, right? It should not get exposed the information critical and that securities. It should not be a breach also. So we do take care those securities things also. Then we talks about zero DPPM and zero defects ZD we call. It's not listed here. So where what we trying to do? Okay, once we are shipping the chip, it's working very well. Fine, no issue. In all our process, all our manufacturing, try time, 3T, all working well. What about after 5 years? The transistor starts slow, right? 5 years. After 10 years, can somebody can throw a car? If we talks about Indian market, we are not able to ready to throw over 15-year-old car. Or somebody will willing to throw that after 5 years? No, we cannot afford it. So we are not claiming that this car will work only for 5 years, right? It minimum to be work for 15 years. But now effect if this are zero DPPM when we are shipping, but after down the line of 3 year 4 years, this car having the manufacturing those latent defects which start slowing the transistor and then it's malfunctioning. There can be, we call them as a zero defect ZD. So we have all and do testing lot of which we call the VLV, very low voltage testing. So at that transistor threshold level, we do and test if any manufacturing defect and which can become potentially after a couple of years. So we try to activate that kind of defect, creating those environments, those tests to ensure getting them detected at the manufacturing because it's a 10 rule of 10, right? For dollar. So if it's detecting at over place, then it might be 500 or $50 kind of rate. But once it's shipped after 5 year, companies recalling all their company, then we can see that what will be the cost of it. Okay. So that's all I have for today. So maybe we can take the questions.
Yes, everyone. Uh, Please ask the questions if you have any. You may type the questions in the chat box, or you may raise your hand. We can give you the mic so that you can ask directly. Full aware is not clear from Mr. Sai Kumar. Sir, please having the question.
Okay. So basically, what we are trying to do is with cell awares are we were talking about this transistor level, right? So this very easy to visualize. Okay, what is you are applying on A and B, and then what you are able to see on the output. Suppose on the C pin of this gate, right? It's a simple truth table and AND gate. How this looks like at the transistor level. Once it map, it goes like this kind of transistor level, and then that transistor also goes to be into the FinFET layers like this. So we are talking the cell aware is a defect between those FinFET layers. So it's a library set which models accordingly for them. So we have all these rather than if we are talking non-cell aware, then it's a three gates, right? So these are the three gates only, three inputs, two input and one output. We are seeing the 6 volts. But now it will be more FinFETs. Between them also there can be defects like this.
टेक वाला हाँ अभी तक तो फोन ही आ रहे हैं मेरे पास मैंने कहा तो कुछ
Okay.
है नहीं मेरे पास। कैसे उसको
Anyone have further?
पता नहीं हो सकता है उनके पास होगा, क्योंकि वो तो डीपीजीसी है ना उनके पास होगा। मेरे पास तो ऐसा ही कुछ इनपुट था कि अगस्त में
Okay.
अच्छा अच्छा
Any other question?
क्लासेस हैं तो yes any more question I'm sorry any more question do you have I'm so sorry so if you have any more question we may ask otherwise let us conclude so thank you so much sir for your insightful talk and it was really very research
Okay. Thank you. Thank you, everyone.
great and what are the issues like we are working at 5 nanometer technology if people are shifting towards 3 nanometer technology you rightly pointed out that there is a yield is decreasing more than 50%. So that is going to create an issue. So yeah, so that is the key thing. All the fraternity would like to know about what the current trends are going on in the industry, and they will get uh, benefits of this while their work and while making the other students skillful regarding. Hello.
Hello.
Yeah.
Yeah.
Yeah. Thank you so much, sir.
Thank you.
Gaurav, are you listening?
Yes, ma'am.
So let us conclude the session and let us meet 6 p.m. in the evening. Okay.
Okay, ma'am. Okay.
Thanks.
Thank you, ma'am. Thank you, sir.
Okay. Thank you, everyone. Let us meet at 6 p.m. in the evening. Bye.